Welcome back to Topics in Statics. This time we're going to talk about frames and machines. We're getting away from trusses. Right, these are different types of structures that frames and machines are pin connected, but they're multi-force members. Right, in a truss, we assume that all the members were two-force members. In frames and machines, that's no longer true. They could be multi-force members. Frames are just structures used to support loads, and machines contain moving parts, things like pliers, things like that. Basic procedure for analysis, very similar to trusses. Draw the free body diagram. Now, for frames and machines, it could be the entire frame or machine, or it could just be a part of it, or each of its members, or it's easiest if we identify two force members early because they have equal, opposite, and collinear forces. They simplify things, determine the sense of the forces, count the unknowns, compare to the equations of equilibrium available. Remember, in 2D, there's only 3 equations for each member, and then solve the equations. Pretty straightforward. So let's try a problem. Here's a frame. The frame supports an external load and moment. Right? Notice that it's got a moment applied to it. Find the horizontal and vertical components of the pin reactions at C and the magnitude of the reaction at B. So the first thing I would notice is that there's 2 pieces to this frame. There's the piece BC and the piece AB. Member AB is a 2-force member. Why is that true? Because it's got 2 pins on it and there's no external forces applied anywhere else. So AB is a 2-force member. I'm going to write that down just to remind me. In fact, I may want to draw a triangle over here. Right, this is going to be 1, this is going to be 3, so this is square root of 10. So now, what's the next step? I would say the next thing is I'm going to draw a free body diagram of BC. So here's member BC. And it's as complicated as I'm going to make my picture of BC look. It's got a force applied here. This is a 400 Newton applied force. It's also got a couple moment, which is 800 Newton meters. It's pin connected up here at C, so it's got X and Y components. But now what about down here at B? Well, it's connected to member AB. Therefore, this force down here at AB is going to be in the direction of AB. Right, so I could put a right, this side's 1, this side's 3, to remind me what that triangle looks like. So now what do I do? So now I would say, okay, I want to look at my equations of equilibrium. Remember, BC is not moving, so it's in equilibrium. So let's calculate the moments about C. The sum of the moments about C has to be equal to 0. So what is the sum of the moments about C? So the sum of the moments about C is going to be, all right, I'm going to break FAB up into components. So the x component, I get 3 over the square root of 10 times FAB times 1 meter. That's the x component of FAB times the distance below C. That's going to make it rotate clockwise. Then I get the other component, the y component of FAB. That's a distance of 3 meters, and that's also going to make it rotate counterclockwise, or sorry, clockwise. I've got that 800 Newton meter, makes it rotate counterclockwise. And then I've got the applied force. This is Newton meters. The applied force, which is 2 meters from A. And all that has to add up to 0. And then I solve for FAB. And if I solve all that, I get 843.3 newtons. Or I could just say FAB is equal to 843, 3 significant digits. So that's the magnitude of the reaction at B. That's part of what they asked me. So now I'm going to use, I'm still looking at this same free body diagram. And I've still got okay, so now I'm going to use the sum of the forces X. So the sum of the forces X, I get Cx minus 843.3 newtons. That's FAB. The X component is going to be 3 over the square root of 10. And that's all the forces in the X direction. So Cx is equal to 800 newtons to the right. I do the sum of the forces in the y direction equals 0. I get Cy plus 843.3 newtons. Y component is 1 over the square root of 10. And then minus 400 newtons. And I find Cy is 133 newtons up. And that's what they asked me for, I believe. Horizontal and vertical components of the pin reactions at C and the magnitude of the reaction at B. That's what it asked for, and that's what we got. So let's try another problem. This one's a little different. This one's a machine. It's a wall crane, supports an external load of 700 pounds over there on the hook at right. Find the force in the cable at winch motor W and the horizontal and vertical components of pin reactions at A, B, C, and D. So where to begin? The place to begin is at that applied load. And what I'm going to do is I'm going to look at pulley E. So pulley E. I've got this load here, which is 700 pounds pulling down, and then there's 2 ropes pulling up. It's the same rope, so that's the same tension. So that tells me that T is 350 pounds. tension in that rope. And that's going to be true everywhere in that rope. The tension is 350 pounds. So now what do we do? So now let's look at pulley C. So I look at pulley C. There's pulley C. I guess I need to make these in red. So I've got a tension pulling down this way. I've got a tension pulling over this way. And then I've got pin reactions at the center, support reactions. So I'm going to have a CY and CX. And each of those pin reactions is going to be 350 pounds. Kind of obvious. So CX is equal to 350 pounds. And CY is equal to 350 pounds. Let's put arrows. This one's to the right and this one's up. Okay. That's nice. I like that. So now what? Now let's look at pulley B. Pulley B, if I look at it, I've got, what have I got? I've got a tension pulling this way and a tension pulling this way. Both of those are T. And this angle is 30 degrees. And then I've got two forces. Let's see, this force, I've got a BY pointing that way, and then BX is going to point to the left because the tension pointing down produces less X component than the one to the right. So now some of the forces X tells me I get minus BX, I get minus 350 pounds times sine of 30 degrees. And then plus 350 pounds equals 0. Solve that for BX. I get BX is 175 pounds. And I do the sum of the forces. Y equals 0. I get BY minus 350 pounds times the cosine of 30 degrees. And that's equal to 0, so BY is 303.1 pounds. So let's spruce things up a little bit. Here's one answer, here's one answer, here's two more answers. Right, they're asking for the pin reactions at A, B, C, and D. So there's pin reactions at C, pin reactions at B. So I still need pin reactions at A and B, and the force in the cable at the winch motor W. Well, we found the force in the cable motor, so that's this one right here. So now, what are we going to do? So now let's move on. Let's draw a free body diagram of member ABC. Right, this is this whole beam that goes from A, goes through B, and goes to C. And what are the forces acting on this thing? Well, I've got pin reactions at A. So I've got an AY and an AX. I've got pin reactions at B, which are the opposite of what they were on the pulley. So I'm going to get pin reaction this way and this way. And pin reactions at C, which are the opposite of what was on the pulley. So I'll get a force this way and this way. Also at B, I've got a force due to that member there, which points along that direction, because BD is a two-force member, right? The only forces applied to it are at the pins, and so it's just a two-force member. So I do the sum of the moments. So now I'm going to do sum of the moments about A equals 0, and from that I get TBD is 2,409 pounds. I do the sum of the forces X equals 0, which gives me AX equals 1,880 pounds. And I do sum of the forces Y equals 0, which gives me AY is minus 700 pounds. In other words, it points down. And that's enough for this. This video has gone on long enough. So next time, we'll talk about internal effects in beams.